Good afternoon, everyone. Sorry for the slight delay getting started. Thanks for joining this session on ALARP for engineers. I'll just introduce myself and Keith before we get started. Both Keith and I are from the IMechE Safety and Reliability Group, which is tasked with, amongst other things, raising awareness for sort of safety relevant sort of aspects of engineering. We hold an annual ALARP conference, which is always well attended. And we sort of see people from diverse sectors trying to get to grips with the LARP. And a sort of running theme through that has been, a very simple concept is actually very challenging to work with on a day-to-day basis. And I think we're expecting something like 200 and 300 or some of that order people joining this webinar. I think just reinforces the point that it's an important topic for engineers. And this specific webinar probably got roots back to around 3 years ago when the group was reflecting on the guidance that was out there to help engineers work their way through the ALARP concept, and the recognition that we felt there was a potential gap. We then embarked on an initiative to develop a comprehensive resource, and throughout that process engaged widely with sort of multiple sectors and also people from the legal profession. Maybe some people on this call that have contributed to that. So if you did, then that was appreciated. Keith, who did most of the work on the document, which you'll go through, is going to present it. And we'll hand over to him now. I think I'll just say a couple of other things before we start, though. The plan is to take all the questions at the end. I think we're going to try and get through this within 45 minutes. It will give us a healthy amount of time to deal with questions. The session is deliberately thought-provoking, so we are expecting a number of comments coming through. So we'll have adequate time to deal with those at the end. So yeah, with that, I'll hand over to Keith.
Yes, thanks, Steve. And good morning, everybody. Welcome to this webinar on ALARP. As Steve says, we had problems with a lot of the current guidance out in industry and so on. And it's basically because of misinterpretations of the law, and the judiciary have issued their own guidance, which to a certain degree conflicts. And therefore we needed to sort some of these issues and bring out an up-to-date set of guidance that would clarify the issues. There were also a number of things with ambiguities, assumptions, and even myths in the safety engineering area that we needed to clear up. And so the document covers a number of issues. But the primary one that has been most contentious, I think, is regarding prediction. So I will talk about that in a bit more detail. So the backstory to all of this happened decades ago when I was a safety engineer on a Coma plant, and we had an explosion in our water system, which was rather surprising because the risk contours that we'd created for the plant, and due to our analyses, showed that it would be thousands of times more likely to have an explosion in other areas than this. And we began to realize that the QRA that we were doing had misled us to a large degree, and it had told us essentially what was obvious anyway, that those areas where there were highest pressures and there was most density of equipment were the highest risk. We didn't need a sophisticated QRA model to tell us that. But I think the thing that bothered us most of all, certainly bothered me, was that I realized the QRA was actually a root cause of this accident because it had focused our attention on the wrong areas. We would have been better off with a random number generator. So this raised a number of questions in my mind. Firstly, is risk prediction beneficial in any way? There must be some pluses for it, and we needed to identify what they were. How should we define the hazards? We hadn't defined the hazard properly in this case because the separation system had failed to separate hydrocarbons from the water. The hydrocarbons had gone through to the drains, had flashed off inside a building and caused an explosion. And finally, we hadn't really established that we got enough barriers to this thing and we hadn't evaluated the barriers in sufficient detail to understand that there was only one thing preventing it. So I want to try and answer these questions in this presentation. Now, first of all, I want to talk about prediction, and I want to go into some detail because it's really important that safety engineers understand some of the principles I'm going to talk about. The mathematician Laplace said probability is a mark of our ignorance, and he was perfectly correct, because if we know everything about a subject, then we know what the outcome will be, and there is no risk. But if we have a deficit of knowledge, then that will be the area where the risk exists, the probability, if you like. So we could express that as a kind of liquid in a jug, where the liquid is our knowledge and the ignorance is the space above. And the way to represent that ignorance is either using statistics or prediction, which will quantify the problem, but they won't explain it. So I want to start off with, I need to define two things, statistics itself and complex systems, before we can then go deeper. So let's look at what I like to call robust statistics, and they need to meet 4 criteria. Firstly, they need to be representative. Obviously, what you're measuring has to be representative of what you're interested in, so it has to be a like for like. They have to be statistically significant, so you have to have enough sample points, maybe hundreds or even thousands, to be confident enough that your results are accurate. They also have to be random. Now, this is an interesting one, because one could argue that nothing is random. If we flick a coin, then the coin only follows the laws of physics. So if we knew the rotational momentum, if we knew the air density, the texture and height of what it would land on, then we could technically work it out. But of course, we don't know that. We don't have that knowledge. And nor do we have control. There is nobody that can flick a coin and decide which way it's going to land up. So we neither have knowledge or control, and therefore we can realistically say that is a random event from our perspective. Finally, it has to be ergodic, and what this means is that if we flick the coin, one coin 1,000 times, we would expect the same result that if we flicked 1,000 coins once. The second definition I want to talk about is system complexity. A simple system is one where an observer can recognize the variables and their effects. A complex system is one where this cannot be done. So let's have a look at a simple system. This might be a stress in a beam, or deciding whether a beam can take a load. There are about 6 variables here, and once we know them, we can calculate quite accurately whether the beam could take the load. But we could also use engineering judgment, probably within an order of magnitude, of whether it can take a certain size of load. So engineering judgment is actually quite effective. Another system might be crossing the road. All we need to know is the speed and distance of the vehicles and how long it would take us to cross the road, and we can make a reasonable judgment that that is safe. So we can use judgment for simple systems. For complex systems, though, it's a different matter. They may have more variables. I've only drawn 6 here, but there could be many more. It could be any type of system, mechanical, instrument, socio-technical, or whatever. But the variables tend to have interrelationships, and those interrelationships can be nonlinear, they can be binary, Boolean, exponential, and so on. And this creates what is a potentially chaotic system. So we have this kind of butterfly effect where a small change in one variable can effectively change the whole output of the system. And there can be a number of these in our system to affect us. So let's just look at an example of this. These 2 planes are essentially the same, except one has different engines, and it has a system called MCAS, Maneuver Control Augmentation System. And the difference, as you probably guessed, is that the one on the left is the Boeing 737 MAX 8, and the one on the right is the Boeing 737-800. The 800 has a very good safety record, years of experience, and is a fine aircraft. But the one on the left crashed twice shortly after its introduction, killing all on board. Now, we can't say what the risk differences between those two aircraft are precisely, but it's obvious that the 737 MAX 8's risks were many orders of magnitude higher than the 800 because of that one small problem. So if we represent that with our jug of knowledge, the 737-800, we had years of experience, plenty of knowledge on it. But when we inserted this MCAS system, which was actually considered to be non-safety critical, as it was supposed to only affect the feel of the controls, actually turned out to have a butterfly effect and dramatically increased the risks. We therefore have to conclude that there's no real relationship between the amount of knowledge and the amount of risk. It can be the smallest deficit of knowledge can lead to huge increases of risk. And virtually all engineered systems are complex because they're unique. And so the risk can never be judged. And this is an important point. So I want to look now at two ways of solving an ALARP problem. We can either do it qualitatively or quantitatively, or a bit of both. So the question is, let's look at the quantified risk analysis approach, QRA, and what I call the well-reasoned argument, WRA. So first of all, let's look at risk matrices and take simple systems. So a simple system might be drilling a hole in a wall. And we might say, okay, well, the risk here is we could hit an electric cable. So first thing we'll do is check for electric cable routes. We could also get drill cuttings in our eye, so we'll wear safety glasses. And we'll make sure we're standing on something safe so we don't fall over. We've got a sturdy base. What we've done now is we've just demonstrated a LARP. We haven't filled that jug, but we've filled it to the level that's reasonably practicable. That's what the law requires. And we've demonstrated a LARP. So the question is, what does this risk matrix on the left contribute to that process? I've worked on these things for all my life, and I still remain uncertain of how they can contribute in any way. I think they can possibly deceive, kid ourselves, but and of course, you could never take one of these into court to defend yourself, because no lawyer would, no self-respecting lawyer would take one in, because you can't defend it. So let's look at complex systems then and see how they work with risk matrices. So the complex system, we could take a number of accidents that we've seen around the world, major accidents, and the one thing that's obvious is they all fit into the right-hand column. There would be multiple fatalities, that's clear enough, but where would we have put them? Well, we would have put them at the bottom because we think they're very unlikely. And this is the point, really. It's about what you think. And anybody that classes a risk as low could well be just saying they're ignorant of the risk of the actual causes, or they're just optimistic. So a better terminology for these risk matrices might be obvious, unclear, and elusive. It is a truism that accidents only happen because someone thinks the risk is low. So why would you dismiss a risk just because you think it is low? The one area that we felt there was a need for these risk matrices was looking at proportionality. Now, the regulator will tell you that you should, your analysis should be proportionate to the risks. But that's a bit of a catch-22, because until you've done the analysis, you wouldn't know what the risks are. So we've simplified that and said, okay, we'll look at the worst reasonably foreseeable consequences on the left, and we'll modify those according to some factors, such as how much potential there is for risk reduction. And that then gives us along the top row there, a level of detail of how much typically we would need to do in the way of analysis. So what we've done, and in the eyes of the law, we have to find the foreseeable hazards. And there's some debate in the document about what is foreseeable. It's mostly based on case law. And then we fill the jug to the level that is reasonably practicable. And in fact, proportionate and reasonably practical are effectively the same thing, used in slightly different contexts. So I want to use a model to look at both QRA and WRA, and I'm going to use the same model for both. This is data, analysis, and decision, and explore what we need in each one. So first of all, if we're doing a QRA, under the data, we've already established that our data needs to be representative, statistically significant, random, and ergodic. Now, different industries collect different data according to what their industries have. For instance, the railways collect things like signals passed at danger as their data, or at least one of their sets of data. In the process industries, we look at loss of containment, and one of the most comprehensive studies done on this has been done by the HSE, who've built a database which is now globally renowned. It's been collected over a period of about 30 years and has thousands of data points. So I'd like to use that as an example to explore the criteria that we're talking about. So their data is split down by different pieces of equipment. That's generally the easiest way to do it. There are other categories, but they're less reliable because you can't always get the data. So typically what we see in the industry is the data split down by equipment types. So the first question is this representative? So let's ask, is this actually causation, or is it just correlation? Now, the reasons that accidents happen are because of things like functional failures, human error, design errors, management of change, or whatever. Accident reports don't say, well, it was an exchanger and therefore it failed. So it's highly questionable that representing the data in this way is in any way representative of the things that cause it. These butterfly effects that we're looking for are therefore eliminated. A second question that we could ask about this data is, what is it actually telling us? Well, if we take the flanges, for example, is this the probability of a leak given that it's a flange, or is it the probability it's a flange given that we have a leak? Now, this is one of the most common errors made in statistics, that people don't recognize the difference between these two things. And huge miscarriages of justice have happened because of precisely this. It's known as the prosecutor's fallacy. So what we want to know is the probability of a leak given that we have a flange. But in order to establish that, we'd have to know how many flanges leaked and how many didn't. Unfortunately, the latter item wasn't collected. We have no knowledge. We don't know how many flanges there are out there in our data set. So it has to be purely guesswork. And I can assure you the guesses are hugely different. But what this does tell us, it tells us the probability that if we have a leak, that it will be a flange. But that's a useless piece of information that nobody would be interested in. The question, though, is that very different to the first piece of information? Well, actually it is, because if we look at the problems that we've seen in various murder trials where this has been investigated in great detail, there are a couple of classic murder trials where both were women and both were found guilty of murder and put away for life. on the basis that the courtroom did not understand the difference between the probability of death, given that the person was innocent, as opposed to the probability the person is innocent, given the death. And the difference between those two things was, in one case, 1 billion times different, and in the second case, 10 billion times different. And they drew completely the opposite conclusions. It took years to have those women freed, once the academics had actually sorted the problems and were able to explain it to the courts. So let's assume that as an engineer, we're asked to calculate the thickness of a plank of wood so that we can cross a pond or a ditch. If we got it wrong by 9 or 10 orders of magnitude, we would calculate that the plank should be thicker than the diameter of planet Earth. This gives you some idea that we cannot sense check risk predictions. Errors of 10 billion times have been missed. We may be able to sense check our normal engineering calculations, but not these. So we can ask yet another question about this. What we note is that most of these incidents were quite innocuous. They didn't actually cause any injury to anyone. And there was only a handful of losses of containment that led to harm to people. And so 99% of the leaks were for different reasons to those that did cause injury. So therefore, there were things like weeps and seeps, corrosion, pitting, or a bit of wear and tear on a valve stem, and they're never going to cause a major accident. So the data is not representative for 3 fundamental reasons. So I could stop here and just say, well, okay, we've made the point, but let's go on anyway. Let's look at, are they statistically significant? Well, we've already established that there was only a handful of accidents that caused any kind of harm to people, so they're not statistically significant either. Are they random? Well, with randomness, if you're producing a probabilistic model, then your data has to be random by definition. But what were the reasons that those leaks that caused injury or death? They were due to things like failed isolation, overpressure of the system, exothermic reactions or dropped objects and so on. But these things are not random. They are the things that we as engineers can control, that we can manage during the design of a product. So one can't regard them as random. We could argue that an exchanger is random because we can't control it. But then again, the exchange is not relevant, as we've already seen. So is this data ergodic? Well, if we take one of the biggest accidents that we've ever had, the Piper Alpha, which killed 167 people, that was a flange that had been left undone. And the question is, was it ergodic? Well, the reasons for the accident were problems with shift handover procedure, permit to work, isolation procedures, and visibility of the valve. The valve wasn't actually on the skid, it was somewhere else. So the skid looked perfectly serviceable, and that's why people tried to start it up. So do these factors apply to any other of the thousands of flanges on that platform? No, they don't. So clearly, this data is not ergodic. Effectively, the risk on this flange is diluted by a factor of thousands of times being absorbed into the rest of the data. So coming back to our model now, we can now say that the data is not representative, statistically significant, random, or ergodic. And what we've done effectively is to eliminate those very butterfly effects that we want to know about. They are the things that cause the risks, and we've effectively eliminated them. And the reason for that is because what we do is we actually have to scavenge data. Unlike scientific processes or market research, where we carefully define the data and collect it according to a very disciplined process, We can't do that. We have to scavenge data because we're looking at rare events. We count what we can count, we don't count what does count. And that basically means garbage in, garbage out. So the next stage is we have to analyze it. We have to try and convert this data into something useful that helps us make a decision. And so what we need is some kind of accurate algorithm that will simulate our complex system. Now, I want to introduce you to Alice and her daughter Elise. Alice actually has 2 children. So what is the probability that her other child is a girl? I'd like you to type your answer into the Q&A now, please. Nice simple one for you there. Fractions or percentages, anything you like will do. I can't see that. Hopefully Steve will tell me what's coming in as you type. I don't know if I can hear Steve. No, I can't hear Steve.
Hi, Nathan. Yeah, I can't see questions coming at the moment. Yeah, so I think what Keith's looking for then is attendee questions. If you could put your sort of view of the answer to that question Keith poses, then I can see them come through.
Maybe people are reluctant to type.
I'm getting them coming through. So there's a bulk of them at 50%. There's one at 51%. There's one at 25.
Yeah. Right. Now, well, sorry to tell you, you've all got it wrong. Everybody failed on that one. The answer is actually 1/3. And the reason I've used this example is to show you that even with a simple question, we can make horribly wrong estimates or understandings, calculations of risk. And if literally everyone on this has made the wrong decision on a simple question like this, one has to ask how we could ever analyze the risks on a nuclear power station, for argument's sake, which is infinitely more complex. I'm not going to tell you why you got this one wrong. So you can, when you go home this evening, instead of doing a Sudoku, you can sit down and see if you can work out why the probability was 1/3 and not 1/2 as you thought. It helps us, it's 2 conclusions that we can draw from this. Probability areas are extraordinarily difficult to identify, even for experts. And I can assure you that many of the Harvard professors in mathematics got this one wrong. But even if you know they exist, even if you're told it's wrong, then it's difficult to find. It still doesn't help you find the errors. But worst of all, there's no incentive to check. I mean, if you build a model like this, where's the incentive? The person selling the model has no particular interest in proving himself wrong. The person buying the model would never have the knowledge or understanding to be able to check it. So it easily gets by. So what we've done, we've created an algorithm that's effectively a bunch of hypotheses, judgments, simplifications of a complex system, and we've omitted critical data. So instead of putting those butterflies in, we further remove the butterflies from the system. Now, we could argue, the next question is, can QRA identify a hazard? And this has always rather surprised me that people think it can. An algorithm only does what you tell it to do. It won't tap you on the shoulder and say, oh, you missed this, or you need to think about that. I listened to a very interesting seminar only a few weeks ago, a webinar it was, describing how to mathematically model complex systems in nuclear power stations. And a young woman a very smart young woman who understood all sorts of complex things like Markov chains and Petri networks. And she'd lost me very quickly. But at the end, I asked her a question. could your model have identified the problems in 3 Mile Island? She thought about it and said, well, yes, if I'd modelled them. But of course, that's the point, isn't it? If you'd modelled it. The problem with 3 Mile Island, it had a feedback loop which didn't actually work as we thought. And so it was giving wrong information. That is a problem that can be solved by an engineer, but it can't be solved by a mathematician. The mathematician will only model what you tell them to model. So these models aren't going to tell you anything you didn't already know. Finally, can we verify it? Well, let's say that we conclude that this nuclear power station is going to have a meltdown once every million years. We would have to operate hundreds of identical nuclear power stations for millions of years before we had enough data to prove it. So you will never verify it. That makes this whole thing totally unaccountable because, and it's rather attractive business to be in because nobody can ever prove you wrong in that sense. However, so what we get out of all of this ultimately is we get a low risk belief because we've eliminated the butterflies and so on. And we're more or less producing perhaps averages at the best. I learned this from my event on my site, but I've also managed to establish over the years some other major accidents where QRA was done and led to the wrong decision. It's not always possible to tell because the accident reports don't always say whether QRA was done, but these 6, it was done. On the Boeing 737 MAX 8, there was a QRA that said it was safe to fly. Now, I haven't seen that QRA, but I can be absolutely confident that it did not model the MCAS system. If it had modeled the MCAS system, we would have known the risks were high. But in order to model it, we would have had to understood it, and therefore we wouldn't needed to have modeled it. This leads us to a thing called the risk prediction paradox. Without understanding the reasons for failure, risk prediction is simply guesswork. But if those reasons are understood, then prediction has no purpose. It's one of those sort of fairly obvious things that seems to have eluded the safety engineering discipline for many years. So another lesson from this is that numerical arguments must be based on a well-reasoned argument. Otherwise, they're of no value. And I put a small caveat at the bottom, but all robust statistics, which can only be modified by sound Bayesian principles. This is a subject that I could have spent a lot of time on, but the problem with Bayesian principles is that they might work well in sort of typical day-to-day ranges, sort of between 10 and 90%, but they don't work for rare events. So if your probability is like 1 in 1,000 or 1 in a million, your errors can be very similar. And this is why we got the errors in the court cases that I talked about earlier. Bayesian principles are not really applicable for this kind of thing. Another one of the accidents in that list was Ladbroke Grove, where a QRA was used to justify not having an automatic train protection system, which would have prevented this accident, which killed 31 people and injured 250. In reality, the problem was that the signal involved had 3 butterfly effects. First, it was beyond a bridge, so you had to go through under the bridge before you could see the signal, so you were virtually on top of it. There were also power cables that were obscuring the view. And finally, the track was on a bend with a number of other tracks, so it was difficult to see which signal related to which track. Now, those 3 things put together, those 3 butterfly effects, could have meant that the risk on that signal was higher than everything else in the UK. We will never know. But they knew about those three problems and they didn't fix them. And that's why the accident happened. QRA is not a solution. So we've now got our data. How do we go about making decisions? Well, the fundamental of making decisions, if you have two mutually exclusive options and you have to decide between one and the other, then if you've got robust statistics for them, fine. We can say, if we're going to travel by, if we're going to move a load by road or rail, we have statistics and we have costs. We can even do a cost benefit analysis. But unfortunately, with engineering problems where we are developing a uniquely engineered system, you'll never have that information. And so the only thing is to look at both options and identify the hazards, the causes, and the consequences, the differences between them, and then produce a well-reasoned argument for your decision, which you would be prepared to stand up in court and defend in the event of an accident. Now, the biggest criticism that we've had about our work is that people continuously tell us, well, we've been using cost benefit analysis and QRA for many decades, and it's been perfectly good for us. Well, let's explore that in a little bit more detail. Let's say we have option A, which is a risk of one in 1,000, and option B, which is a risk of 1 in 10,000. Now, obviously, we would want to go for option B because the risk is 10 times lower. But let's say we make a mistake. Let's say we get it wrong and we pick option A instead. What is the chance that the wrong decision will have consequences? Well, actually, it's only 1 in 1,000 because it's unlikely to happen, this thing, even so. So we can go through life making 999 decisions wrongly out of 1,000 and get away with it by chance alone. And it has to be said that most of us probably do succeed by chance in our careers because we're dealing with things that might never come our way. What all this low risk belief systems cause is problems with, firstly, a thing called probative blindness. Once somebody has told you that the risks are low and given you a number, you are highly unlikely to challenge that further. We have this quantification bias, and there are many other cognitive biases that influence what we're doing here. I could spend another webinar just talking about these, but I don't have time. I've given some useful reading links here. There's a couple of classic books, but the one I'd thoroughly recommend is The Intelligence Trap by David Robson. I think that it summarizes most of the other research and is a very readable book. So it leaves us with the question, can we find any other reasons why QRA could have benefited? I have a sort of standard list of accidents that I use, as shown here, that come from different industries, different parts of the world, etc., and is useful for testing any theory on. And so I've asked the question of each one of these, could QRA have benefited these or reduced the risks or helped in any way had it been done prior? And the answer was no in every single case. But what I can tell you is that 20% of these, QRA was a contributory factor. It was a root cause that led to the deaths of many hundreds of people. Now, I have read numerous papers on QRA, and to my surprise, and there are plenty of them out there, but none of them have done anything other than what I would regard as a fairly superficial address of the subject. I believe that my work is the first time that anyone has done a proper technical mathematical assessment of QRA models. And when you consider that they've been complicit in so many deaths, it is a staggering thought that nobody has ever done this work before. Because there was no incentive, we almost have a perfect storm that says, why would you? So that's the technical argument. Let's just look at the legal side. And the real myth arrives from this carrot diagram, which most of us will know and be familiar with. And it has no substance in law whatsoever. There is no such thing as intolerable risks in the eyes of the law, and there's no such thing as broadly acceptable risks. All risks have to be alarm. It doesn't matter how large or small they are. And the courts have recognized this, and they've come up with their own guidance. And this was brought out about 10 years ago, and it is virtually impossible to meet these criteria with any kind of probabilistic analysis. So what we can say is QRA is a highly deceptive pseudoscience, which has been a root cause for hundreds of deaths. And there is no evidence that it has ever benefited any risk assessment. It is driven by quantification bias, our desire for numbers, the Dunning-Kruger effect, which shows how people with limited knowledge of a subject can make huge mistakes, willful blindness, and motivated reasoning. And the problem is that we as engineers generally don't have enough knowledge to really understand these models and realize the truth about them. So we don't have the confidence to reject them. And that's why I've spent so much time today to try and give you an idea of just how these things go wrong and how ineffective they are, so that you can take a better view in future if you're ever involved with this sort of thing. So now let's apply our same model to the well-reasoned argument, the WRA. In this case, we need, our data has to be the hazards and the consequences, the reasonably foreseeable consequences. Now, I did say that we hadn't identified our hazard properly on our particular plant where we had the explosion. So what I did was to sit down and say, how could I define that for the purposes of hazard assessment using a set of criteria or a model, if you like. And I did this with all those other 30 as well. And I found that I could define any major accident with these 6 criteria: source, context, unsafe condition, escalation factors, outcome, and worst reasonably foreseeable consequences. And I've put some guide words in the second row there to show the sort of things you'd be looking at, and described our problem at the bottom. Now that may be too detailed for many hazards which are not so serious. So what we've done in the document is to give a graduated approach to using the proportionality matrix to determine what level of detail you need to define your hazards in. So that uses the proportionality. Then in our analysis, we need to identify the causes. And these are all the typical tools that we use, such as failure modes effect analysis, systems theoretic process analysis, which is a very effective tool, becoming used much more these days, HAZOP, human factors analysis, safety critical task analysis, etc. But what all of these things do is they identify the butterflies. That's their purpose, is to find butterflies. We also need to know the adequacy of our defenses. That was my third question. Did we have sufficient defenses? One of the interesting things is that James Reason, when he developed the Swiss cheese model, showed both things. The Swiss cheese shows the defense and it shows the weakness, the holes in the defense as well. But what we've done is we've created these things called bow ties on the right-hand side, which only show the defenses. They don't show the weaknesses. So as a graphical illustration, this is highly deceptive. What we want to know and where we want to put the emphasis is on finding weaknesses. So what we've developed is a set of guide words for evaluating these. Things like common mode failure, the availability of the system, whether it can be overridden, whether it fails to safety for the system, or whether the failures are even self-revealing, etc., etc. So this is a good basis to start from to develop guide words for any system that you need to evaluate its weaknesses. So now we have all the information that we need to put together to make our decision. And we can now build a well-reasoned argument. There is, I have to say, a lot of reluctance in engineers to build well-reasoned arguments. It's far easier to trust a model, and I think people shy away from the idea of having to structure a complex argument. But it's necessary. It's necessary if you're ever to understand what you're doing. And a lot of people think, well, maybe you can't. But if you can't, then perhaps you haven't got an argument at all for what you're doing. I gave up QRA 25 years ago, and I've used the well-reasoned argument ever since. I've done some highly controversial things in the oil and gas business, which have changed the way we work. And I've always used a well-reasoned argument, and I've always won my argument, because once you developed it, you know what you've got. It's less susceptible to cognitive biases because it's transparent and verifiable, and most of all, it's legally admissible. Thomas Kuhn, in the classic work, The Structure of Scientific Revolutions, stated that scientific progress only happens because our beliefs fail and we have a crisis. So we would still believe that the sun goes round the earth if it weren't for the fact that the navigation systems will not work on the basis of the sun going around the earth. We had to, Copernicus changed that to the earth going around the sun, and suddenly the ships all started to arrive at the right ports. So the belief was overturned. And all scientific progress actually follows that model, that you have a crisis and you then move on. But what if you can't have a crisis? What if nothing is verifiable, that you can never be disproved wrong? Then how will you ever move forward? The only way is if you have an intelligent debate about a subject and you listen to the logic and apply it and prepared to. Max Planck once said that science only progresses one funeral at a time, because lots of people have personal skin in the game. Their reputation is based on it. It's the way we've done things for years and years, and the knowledge gets handed down from generation to generation, so things don't change. So I'm going to leave you with a question. If someone asks you what your risks are, would you provide a QRA or a WRA? And if QRA, then why? Thank you very much.
Thanks, Keith. It's really thought-provoking and probably a little provocative, I guess, deliberately so, perhaps. I've just been monitoring the questions as they've been coming in, and I'm trying to cluster them together because we're conscious we're quite short on time. So there's a theme about the argument that we should stop using QRAs because there are examples of when they've been done badly, and also I guess there's a question there about can QRA and well-reasoned arguments coexist? I don't know if you've got any comments on that, Keith.
Well, they can coexist, certainly. I mean, if your QRA is based on a well-reasoned argument, then yes, but quite often the whole idea of doing a QRA is because you haven't got the knowledge or the information that you want, and you're putting numbers together on a very unsound basis. So it is important to realize that we're not knocking any kind of probabilistic analysis. There are ways that you can do it. But in engineering terms, they are actually very few and far between. And so we do need greater knowledge in this area to be able to understand these things. unfortunately, I believe that safety engineers probably haven't had nearly enough training in probabilistic analysis to know when they can or cannot use it.
Okay, thanks, Keith. There's also a few questions of people that seem to agree with you, Keith, and saying that how quickly do you think things will change?
Yeah, that's a great question. How quickly will they change? I think, yeah, we need to talk to the influencers in these areas, and we need to get a lot of the current guidance changed. Now that we've got our document out, it at least challenges that other guidance. But the next stage would be to try and get that other guidance changed or taken away. So it's a difficult one. Of course, it's always easier to produce a number than it is to produce a well-reasoned argument. So there's always an incentive to go that way if you think you can, and if you think you can get away with it.
Okay, thanks. And what about industries that specify specific allowable rates for failure? Do you think that creates some of the problems you've been describing, Keith?
Yeah, failure rates are an interesting one. It depends if you're talking about reliability, then reliabilities can often be proven statistically. So you can have robust statistics for a reliability. I'm often a little bit disappointed that we often lump safety and reliability in the same box. Something can be safe but not reliable, or it can be reliable but not safe. So there is an overlap, obviously. But yes, we can certainly look at reliabilities, and we often do this with SIL assessments in looking at instrumented protective functions, say like tank overflow protection and so on. The reliabilities may be reasonably accurate and may be acceptable accuracy, but it's the initiating event that you often don't know. And so sometimes you're talking about initiating an event that may happen 2 or 3 times a day, so you've got statistics for that. But if you're looking at, say, an explosion that may happen once every 10 years, 1,000 years, 100,000 years, you don't know, and you're back to the same problem again. So this is why I say we need to understand where we can and cannot apply this sort of thing.
That's good. I'll just take there's one more question I'll ask, and then we'll close. And it's a really good one. How do we use well-reasoned arguments when we're becoming more data-driven?
Yeah. I think data, there's enormous emphasis on big data these days, and people collecting an awful, we see this in social media platforms and how they use vast quantities of big data to work things. And generally it works because most of the time you'll be right, but some of the time you'll be wrong. The problem is with safety and with major accidents, we're interested in the very few times that we might be wrong, not the large percentage of times that we may be right. We're trying to avoid that 1 in a million, 1 in 1,000 event. And this is where the whole theory of sort of big data doesn't work in safety. You can't take those principles and just drag them across. And I agree, it's a problem for us in our industry, because a lot of people see this as the way forward. And just because you've collected a lot of data doesn't mean it's representative statistically. Well, it'd be statistically significant because it's big data, but it won't be representative, won't necessarily be random or ergodic. So it may have little relevance. I hope that answers the question.
Yeah, thanks, Keith. Yes, I think we'll close it there. Sort of for time now. There's a couple of comments about the document itself. So that document has been issued already. I think it was actually issued last summer. I and we're intending to have an annual refresh of that. And within the document which is available on the Amaki website, there's some details about how you can provide feedback and engage. So yeah, the intention there is that it's a document that does generate feedback, and to move this topic on. So if anybody wants to comment directly on the document, please follow the route that's outlined within it. So I think again we've sort of seen that ALARP is a subject that people struggle with, to sort of demonstrate and achieve. We'll continue this conversation at our ALARP conference, which is on the 12th of October, which is always a good event with people from a variety of different sectors giving their view on this topic. So yeah, look out for that on the Amaki website. So I'll just close with sort of thanking the Amaki and also Keith for his time putting together the slides and going through them today. So do you want to say any closing words, Keith?
No, thanks very much, Steve. And I would say to anyone, in the front of the document, it actually says if you have any comments, the details are given in the forward of the document. So you're welcome to feedback your thoughts. We'd love to hear them. But thanks for your time, everyone.